Now, one other point of note is that the area of the A band, of the dark band, which does not contain actin filaments, into which the actin filaments do not extend, is called the H band. And this is important because the H band is the band that decreases in size along with the I band during contraction of muscle. Oops. Now, when a sarcomere contracts, the Z lines, Z discs, get pulled in towards the center of the sarcomere from each side. The length of the A band does not change. The length of the actin filaments does not change. They just get pulled in towards the center of the sarcomere, and we'll look at how this happens in a moment. But what does change is the width of the H band as the actin filaments get pulled further and further into the dark A band. The width of the H band decreases, and the width of the I band, the myosin-free part of a sarcomere, also decreases, as you can see here. Now, let's look at how this happens. This is a slightly different diagram than in your notes, and I'm not sure that I really like it anymore than the other one, but it does show some features, so I'm going to work with it. I like to start down here with the fact that myosin, which is a large polymerized molecule, consists of a long chain, and then two heads which stick out from the myosin chain at very precise angles. And what is important is that these myosin heads are ATPases. That is, they split ATP into ADP and PI. And as you remember from your biochemistry, when the terminal phosphate of ATP is hydrolyzed, a lot of energy is released and made available for work. When the myosin head splits ATP, the ADP and PI remain bound to the myosin head, and the energy that is released is conserved in this myosin head ADP-PI complex. So now let's go up to number 1 here and remind you that when a nerve impulse arrives on a muscle fiber, that nerve impulse is transmitted down the sarcolemma or plasma membrane, and then enters the muscle fiber and surrounds each muscle fibril within the fiber, forming these T-tubules, which are just extensions of the sarcolemma. And this occurs, I should have said, at the AI junction. At each AI junction, the sarcoplasmic reticulum is also specialized to form these terminal cisternae, and with one on each side of the T-tubule. And these terminal cisternae are reservoirs for calcium. So calcium stored here waiting to be released. When the neural impulse travels down the T-tubule into the T-tubule, it opens up voltage-gated calcium channels in these terminal cisternae, releasing large amounts of calcium. And as this occurs at both Z discs here and here, the whole sarcomere is flooded with calcium very quickly. This calcium binds to a molecule called troponin, which is covering under in the calcium-free condition is covering the binding site of myosin to actin. So I should have mentioned earlier that when ADP and inorganic phosphate are bound to myosin, that myosin head is not bound to actin. And this is because the binding site that to which myosin would actually bind is blocked by a molecule called troponin. Troponin sits on the actin fibril and blocks the binding site, which is shown here in an unblocked state, which means that the myosin head can't I should have mentioned that in the resting state, when ADP and PI are bound to the myosin head, this myosin head can't bind to a binding site on actin because it is covered by this molecule called tropomyosin. It requires calcium binding to another molecule called troponin to release the tropomyosin and to expose the calcium binding site. And we'll look at this in a bit more detail as we go through this diagram. A nerve impulse travels down the sarcolemma into the myofiber and down the T-tubule, which surrounds each myofibril. This opens voltage-gated channels in the terminal cisternae of the sarcoplasmic reticulum, and calcium flows out of the sarcoplasmic reticulum and floods the sarcomere. As the calcium floods the sarcomere, it binds to this molecule called troponin. And when calcium binds to troponin, it causes the tropomyosin, which is currently blocking the binding site, the myosin binding site on actin, it causes this tropomyosin to move out of the way so that myosin can now bind to the binding site on actin. When myosin binds to the binding site on actin, ADP and PI are released, and the energy that was stored in this complex here causes a conformational change in the structure of the myosin head, and this conformational change pulls the actin filament as the myosin moves from here to here. It pulls the actin filament in towards the middle of the sarcomere. And of course, it's not just one myosin head that is moving, it's many hundreds of myosin heads binding to the actin filaments, which all change shape at the same time, thus pulling the actin filament in towards the head, in towards the middle of. Once this movement is finished, another ATP molecule will bind to the myosin head, causing the myosin head to detach from the actin filament. ATP is hydrolyzed to ADP and PI, and we return to the resting state of sarcomere contraction, of muscle contraction. As long as there's enough calcium present surrounding the sarcomere, this cycle will continue. Calcium will bind to troponin, causing tropomyosin to move away from blocking the myosin binding site. Myosin will bind. Energy will be used to cause a conformational change in the myosin head, and the actin filament will be again pulled in towards the center of the sarcomere. If no ATP is present, then the myosin head can't detach from the actin filament. It's the binding of a new ATP molecule to the myosin head that causes it to detach. And this is the structure, this is the situation called rigor mortis. After death, when no more ATP is present, the muscle will be maintained in this contracted state.